And the first presentation that we'll be going through that we're providing you with is a presentation on the connection between prefabricated elements. So ABC, when we were deciding what presentations to put together first, we thought, well, connections is one of the most important components in ABC. So let's put together one on connections. So ABC, we use prefabricated bridge elements and systems, one of the primary ABC techniques. So that's why connections are important. As I had mentioned before, we try to provide some learning objectives at the beginning of each of these presentations. So in this one, the student should hopefully be able to compare different types of joints that are available between superstructure and substructure elements, and identify the type of connections that would be appropriate for different applications. This presentation kind of focuses on the AASHTO LRFD guide specification provisions for joints. So I'll highlight the different sections and equations throughout the presentation. First, one of the main benefits of ABC and the use of prefabricated elements is the quality of prefabrication, the quality of prefabricated elements. So we use higher quality materials when they're prefabricated, and there's also better quality control. So these are two things to highlight. So feel free to replace these photos. These are from the PCI manufacturing precast video. I liked it because it shows somebody doing some QC, but if you teach steel or another subject, then you can get your own, you can replace these photos as you need to. Next, kind of an introduction to connections. The connections can be used in many different applications between different superstructure, substructure, and foundation elements. I'm just kind of highlighting some of the common or some of the previously used connection details. One common detail is between different prefabricated superstructure elements. So these are adjacent box beams with a UHPC straight bar splice connection. This is a pocket connection and a grouted duct connection. So see the straight bars going into, it's small little duct connectors in the top element. There are a number of different categories for connections, and the ones that I'm showing on this slide are from the AASHTO LRFD guide spec for ABC. So these, I guess, specifications are provided and details on how to design these different connections are in the guide spec. So I highlight some of these in this presentation, but not all. So if you're interested in something that I don't cover, then you can go to the AASHTO LRFD guide spec for ABC for more details. And there are a couple NCHRP reports as well by Mike Kulmo. So the first main category is cast in place closure joints using lapped bar reinforcement. So here are two different common applications between full depth precast deck panels. They can be used as shown here, or between full pre-decked elements, or one example being the decked bulb T. So here you can see the connection there. There are three kind of main types of connections: straight bar, hooked or hoop bar, or headed bar connections. So here are just kind of three cross sections and plan views. So you can either have I guess these are three typical configurations. One is a non-contact lap splice. So the bars coming out of the adjacent elements are at different sections along the plan. Or with a straight bar, you can also have a field-placed reinforcement here connecting two bars extending from the elements. And headed bar, typically you would do a non-contact lap. So on the next couple slides, I'm going to go through it quick. If you're teaching it in class, obviously you can spend a little more time on these, but I'll provide some equations and the reference in the specification, so the reference number. So here are the, I guess, for reinforcing bars and closure joints with straight bar using conventional concrete or high performance concrete. I think it's up to 15 KSI normal weight and I think 10 KSI lightweight. You use the equations given in AASHTO for tension development length. So that's given here. And here are some of the lambda factors. So I guess I kind of wanted to highlight, you know, I teach a precast concrete design class, so connections is a module that I teach within that class. But I also teach reinforced concrete design, and in a reinforced concrete design class, I talk about I talk about some of these ABC connections when I'm talking about development length and bond and anchorage. So you know, I talk about as that an application, and I guess you know I'm showing AASHTO, but you know you could teach. And in bridges, you'd use AASHTO, but you know, in reinforced concrete, I teach ACI, and I mentioned ABC as an application. So anyway, just try to. You don't need to teach a module on connections to be able to include some of these details in your class. So anyway, variable definition, and then here, just some details on if you're using it in a non-contact splice application, there are some requirements on the I guess how close the bars need to be together. So, right, you can have a non-contact lap configuration, or the configuration here where you have a field placed rebar and it's connecting these two, so splicing the two bars together. So obviously a non-contact, you can have a narrower joint. Here is a typical detail from Massachusetts DOT. So you can see here they have the bars extending from each, and the width of the joint would be dependent on the required splice length. The other comment here is with these closure joints, a lot of times shrinkage can be an issue. So I think that Royce is going to talk about shrinkage a little more and some tests that are done with shrinkage, but just you know something to highlight here is if you don't consider shrinkage, you can get some shrinkage cracking in the joint region because you know your deck and your other elements will have already experienced their creep and shrinkage already, and your closure pore you know is restrained on each side and trying to shrink, so you can get some shrinkage cracks. The next category here we have hooked rebar. So here's kind of a typical detail. So we have our hooked or hooped rebar coming from our adjacent panels. I show us a Boulden pipe leveling system. So this system allows you to level these precast panels for your riding surface and kind of easily adjust the height. And then the joint for these can be over the top flange of your steel or concrete girders, and that acts as your bottom form here. And the lap, or yeah, the lap distance is dependent on the AASHTO LRFD development length requirement for hooked bars. So typically these would be in a non-contact lap splice configuration, and the guide spec says they need to be 4 inches apart. So typically it'll be 8 inches apart in a girder so that the bars in the joint will be 4 inches apart. And here's a typical detail from Massachusetts DOT. Headed bars can be used too. So I give similar details on headed bars. You know, same with variable definition equations and some of the criteria. And in the guide spec, there's a specific equation here that's based on the strut that develops between these the heads and the headed bars. So they're assuming that this angle of the strut's 55 degrees. So you take the spacing divided by tangent of 55, and that's where this 0.7 S sub B or S sub B comes from. So I try to provide some additional details on some of the equations where appropriate. And then here's a typical detail from a Washington project. I guess I had some trouble finding in our project database many examples of a headed bar. So anyway, it's at least from the database, it's not as popular as like a hooped or straight bar detail. But here you can see the headed bar and the length of that, which anyway seems a little long, but this was a project back from 2013. So the next main kind of category of these straight bar connections is ultra high performance concrete connections. So this whole section of the guide spec is mainly based on some work done from FHWA. So I give a little reference to that here and work done by Ben Graybill there. So you can see the development length depends only on the bar size. So right now it's not dependent on concrete strength or anything else. They give some minimum required properties for your UHPC and then just vary the development length based on the bar size. So you can see FY less than 75 KSI or between 75 and 100. Here are some of the criteria for that, or further requirements I showed on the previous slide. So, what bar size, what concrete strength, fiber content, and what the detail actually looks like. There's a requirement for minimum cover. So I highlight that here. If you don't meet the minimum cover requirements so that you can get all the fiber orientation that you need around the bars, then you need to increase your development length. And here's the splice length is a portion of the development length. Graybill also has some details specific for number 5 bars. So number 5 bars are commonly used in bridge deck applications. So he did some testing, and you can decrease your cover and still have 8 dB or 10 dB development lengths. So I just highlight that there. And then just UHPC is being used and has been used a lot in different applications. So here are some different applications for the straight bar splice detail from Graybill's work. And as of 2019, Graybill found that there are over 300 different projects utilizing UHPC. So this is continuing to increase as UHPC becomes more available, and non-proprietary UHPCs are bringing down cost. All right, so here we have a couple different connections that are mainly for substructure elements. So the first one that I'm showing is the grouted duct connection here. So we have a reinforcement extending from one element and a duct that's cast, a duct void that's cast into an adjacent element, and then you place the elements together and then backfill with grout. So I guess I've heard some people say that this is it's an easy connection for contractors to get lined up. Precasters are able to use. I guess precasters are typically able to get the ducts in the right position, and it's not a hard connection to do. And I guess I've also heard that it's hard to get a lot of number 11 bars lined up and to connect these to connect 2 elements. So I don't know. I mean, I'm not sure who to believe, but maybe if you're teaching it and you could teach that. I think it would be heavily relying on the contractor experience and the quality of the precast plant or prefabrication plant. So I know there are different levels of precast plants, so I think that would be dependent on that. So anyway, I just wanted to highlight that because to me it does seem like it might be hard to get those bars lined up. But there are equations that are specified in the guide spec for ABC, so I'd highlight that here for development length, and some other details on what type of duct you should use and filling material and things like that. So this work is based on a couple different research projects, so I try to highlight that here. You can see the actual duct in here and then backfilling with the grout to connect them and see what it looks like. And Graybill also did some work with UHPC in the duct. So here you can see the UHPC kind of filled already, and then they're lowering the elements into the ducts. And here's, I tried to give some example projects for these substructure connection projects. So here are some example projects from the ABC project database. The next two main types of connections between substructure elements or pocket and socket connections. So a pocket connection, we have a void in one of the elements and reinforcement extending from the other element. And then you kind of backfill the void with cast in place grout or concrete, and that creates the connection between the two elements. So this is a pocket connection on the left, a socket connection here. You don't have reinforcement between the two elements, so the one of the connecting elements is embedded in the other element. So this is called a socket connection. So here are the guide spec, or some of the details from the guide spec on pocket connections. So pocket and fill, some details on pocket sizing compared to where the reinforcement is. Some details on how long the bar needs to be embedded in the pocket to get the proper connection between the elements. And the variable definition. And then there are also some additional requirements if you're using a pocket connection in a seismic region. So typically, you would have reinforcement around this embedded reinforcement. So confining reinforcement around the embedded reinforcement. And the AASHTO guide spec allows you to kind of use that corrugated steel pipe as your confining reinforcement. So there are equations for calculating the thickness of the pipe depending on what seismic design category you're in. There are additional transverse reinforcement requirements, also depending on the seismic design category. So in a lower seismic design category, you need additional reinforcement in the precast cap around the corrugated metal duct. So you can see some of the bars highlighted here. One of the other kind of mechanisms that, I mean, the behavioral mechanisms that I highlight and you can highlight in class is the kind of shear friction transfer between the cast in place pocket and the corrugated metal duct. So the AASHTO guide spec for ABC gives a neat equation here that's just dependent on the compressive strength of the pocket concrete and the area of the cylindrical void. So give some equations for, give some equations for that here. All right, and here are some samples from the ABC project database. So then the next connection is the socket connection. And as I said, the socket connection is reliant. It doesn't have any reinforcement crossing between the elements. So here you can have it in a cast in place footing, which I guess has been used in different ABC applications. And you can also use it between the two precast elements. So here a precast pile cap and a precast pile. So here are some different requirements from the AASHTO guide spec for the socket location, and some visuals from the guide spec. And again, there's some additional reinforcement that's needed around the socket in the precast cap. So I'm highlighting that additional reinforcement here. So there are equations in the guide spec for the socket length shown here, and that's also based on the tension development length of the reinforcement. And yeah, I guess there's some additional details on the socket connection. So the height, the diameter of this vent where you would insert your grout or concrete, and the overall height of the cap. Here are some sample projects with the socket connection. So in terms of detailing, pocket and socket connections can create a little bit of a challenge. So I highlighted, or I guess it was kind of shown here, but with the pocket or socket, you still need the reinforcement that you need in the cap, but you need to somehow, move it into portions that are precast. So this can lead to bar bundling and a large amount of reinforcement kind of immediately adjacent to the pocket. So that can be one of the detailing challenges. There's an example, or there are examples where not as much reinforcement is needed in the pier cap element. So here there are a lot of piles. There's not as much moment developing in the pier cap, so they could get away with not much reinforcement in the pier cap, and it's not a problem for them. For this NCHRP project done by Saeed at University of Nevada, Reno, they needed to bundle a lot of reinforcement here and here. And I guess, I'm sorry, I misspoke. This specific testing was done under the ABC UTC. So one of the other NCHRP projects done by Restrepo, you can see that they just extended some reinforcement through the pocket here. This isn't the most ideal for constructability because the reinforcement can conflict. So, and it's not possible for socket connections where an element would need to be embedded in there. But this is, another possible option. All right, so anyway, that's some basic information on connections, and I'm going to I will stop the recording and switch it over to Royce, and then I guess we'll start back up for his.